but you're still going to need a critical value here to determine how much bigger than 1 it should be. So we're not actually interested in whether or not it's exactly 1. We're interested in is it much bigger than 1 or is it about 1? Right. So we also went through and reminded you what this terminology is. We said within and between groups are different from within and between subjects, and that's really important to remember. Within and between groups refers to different kinds of variances. Within and between subjects refer to whether the design of the study had the same people in the different groups or different people in the different groups. Make sense? Okay. So this stuff is really foundational. If you don't get this stuff, it's going to be really hard to follow this ANOVA lecture. So make sure that you come back to this later if that's not quite making sense. You walk through and make sure everything follows when you have these definitions. So here's some more terminology we're going to need. We're going to need to know sums of squares. We already know degrees of freedom, but we also need to know these mean squares. So a sum of squares is basically a sum of squared deviations, like the one you used when you calculated variance and standard deviation early in the course. So a mean square is going to be a sum of squares divided by degrees of freedom. So if you just think about the variance you already learned, what is our formula for the variance of a variable? We have a sum, right? What's in the sum?
Xi minus x bar.
Yep, xi. So 1 score minus the mean, and then we square it. We do all of that for each score, and we add them all up with this sum, right? What's in the denominator? Yeah, n minus 1, and as very cleverly pointed out, this was the same as the degrees of freedom we had for our one sample test. We're doing the same thing here when we calculate mean squares. We're going to calculate this, which we're going to call a sum of squares for x, and this is going to be, degrees of freedom for that group. So basically today what we're going to talk about is different kinds of variance. We're going to calculate a variance between groups and a variance within groups. And we will also use, our classic variance here too. This term, it turns out, is going to be our total sum of squares. So that'll make more sense in a minute. But we are basically just going to do this in a couple different ways. So just to kind of remind you of that notation and to introduce kind of a new set of terms to describe it. So the sum of squares is the sum of square deviation scores. The degrees of freedom are the thing that we're going to have to divide by, and that's just basically the number of things that we have that we're using in our calculation minus the number of things we had to calculate. And that's going to get a little bit more complicated this time in terms of figuring out what those degrees of freedom are. And then finally, when we take the ratio of those two things, we end up with a mean square. So when you hear mean square, think the average, basically, of the sum of squares. Because that's effectively what you're doing when you divide by degrees of freedom. You're kind of estimating on average what these square deviations would be. All right, so those are the terms. Here's where we've already seen them. We didn't use this language, but we could easily. And let's look at some more terms or some notation. So in this simple example, right, we only had one data set. So xi was really nice. Is there a question? I see some puzzle points. All right, then we're just going to keep going. So here we only had one data set, and we did everything for that one sample. So I is just very simple and straightforward. However, now we have basically 3 samples. We have group 1, group 2, and group 3, and they all have 4 people in them. So our notation is going to have to get a little bit more complex. So instead of having just xi to describe the people in our one group, we're going to have xij. So I is still the person number, but j is going to be the group number. So when you see, xij, that means we're going to go through the people in this, in each group and each person within each group. So let's look at that. What is the score of person x1, 3?
5.
Yeah, so we go to first to the third group, and then we go down to the first person, and that's 5. And then what about x2, 2?
12.
So we go to the second group and then the second person, that's 12. And then how about x3, 4?
There's no fourth group.
There's no score. That doesn't work. What about x4, 3? 6. Good. So these are the groups. These are the people, and obviously those indices will only go as far as you have groups. All right, so we don't have a group 4, so that one didn't work. All right, let's keep going here. So that's how we notate scores. We're also going to have this term. The bar isn't showing up very well in that slide, but that second one there is x bar j. What do you think that represents? The mean of group J. So x bar 1 is going to be the mean of group 1. X bar 2 is going to be the mean of group 2. X bar 3 is going to be the mean of group 3. And that should be pretty straightforward. And then finally we have one more little bit of notation here for now. We'll have more later. But we're also going to have to introduce the grand mean, which means the mean of all of the scores that you have. So you add up all the people in the control group, all the people in medication 1, all the people in medication 2, and then you just take the average. Or divide by the total number. So that would be, in this case, 3 times 4 is 12, 12 people. Good? Question? Yes?
So there's this score I and group J. Should it be group, score J group I?
No.
Up there you said since x4, 3 seems very simple.
We said there's no 3, 4.
Oh,
Right? So yeah, this is person, and then fortunately you won't usually have to go through and figure out what different indices are. Usually it'll just be written xij, which just means you're going to go through every person in every group. And then x bar j means you're going to go through the mean of each group. And then x bar g is just the grand mean. Okay? Sound good? Thank you for clarifying that. I said something and then erased it and then wrote something different. So I'm happy that we clarified. All right. So let's talk now. I think we have most of the machinery that we need. Let's talk now about conducting these calculations. All right. So the basic steps in this hypothesis test are going to be the same as they've been. We're going to, have to hypothesize. We're going to have to choose our test, just like we did, which in this case will be, fairly easy. You'll have to decide to do an ANOVA, and then you'll have to decide whether the design is within subjects or between subjects. I say it's easy, but it can be challenging. So we'll have to pay attention to that. We'll have to check our assumptions. There are assumptions for this test that are going to be different from what we had in the t-test because we're doing things a little bit differently now. So we're going to have actually a few more assumptions to worry about. Then once we do that, we can calculate our the appropriate test statistic. What is that in this case? The S statistic, yeah. And then we'll either calculate a p-value or look up a critical value and go from there. Most of the time when you're doing this by hand, you'll be using critical values, but I could give you like an ANOVA table that's output from say SPSS or something and say find the p-value in the table, and it's given in the output, so you would need to look it up there. All right, then you need to draw a conclusion from that information, so either the p-value or the critical value, and then interpret your result. I should mention this before I move on. A lot of people had more difficulty than I expected deciding when to reject the null hypothesis. You cannot compare a p-value or an alpha value with a critical value. That doesn't make any sense. So p and alpha are both probabilities. Alpha is some probability that you fix to be like, 2.5% or something in each tail. So far I've sketched my alpha. Alpha has a critical value that corresponds with it. So for example, if this was a z-test, it would be 1.96 minus 1.96 and plus 1.96. So this critical value is referring basically to the same concept as this alpha value. This is just the value on the x-axis that corresponds to the spot where you're cutting off 2.5% in this case. Makes sense? Similarly, when you're calculating a p-value, you have the same distribution you're looking at, but instead of looking at a critical value and an alpha value, you're looking at your test statistic value, so whatever you calculated, sorry, we're using z here. This is the thing you calculated with your z-statistic formula, and in a two-tailed test, your p-value is the area past that, and past the negative version of that. So when you are checking whether or not you should reject or fail to reject your null hypothesis, you can either compare your z value to your critical value, or you can compare your alpha to your p-value. You cannot compare your p-value to your critical value or your alpha to your z-value. Those things don't make any sense. Your alpha and the p-value are always going to be numbers between 0 and 1. Z and your critical value, they could be, anything between 0 and plus or minus infinity. Like, they're numbers, not just probabilities. So it doesn't really make sense to say, oh, well, the critical value was higher than the p-value, therefore we reject or fail to reject. Like, you're comparing apples and oranges. One thing is always going to be less than 1, and the other thing could be anything. So make sure you either compare your p-value to your alpha level. So if the p-value is less than your alpha level, then you reject the null hypothesis. Or you compare your z-value to your critical value. If your z-value or t-value, whatever that you're using, that's higher in this case than your critical value or lower than the negative critical value you would reject. So in this case, it's not. Our p-value is bigger than alpha, and our critical value is more extreme than our z-value, so we would fail to reject in this set of pictures. All right, so just to be clear, compare like to like. Compare probabilities with other probabilities. Compare t or z values with other t or z values, right? Make sense? A surprisingly large number of people mix that up, so that's why I'm going over it with everyone. I apologize for those of you that are like, duh, but some people have different backgrounds and haven't had as much experience with this yet. So yeah, let's keep going. So here we have our ANOVA assumptions. We're going to need to check some of the usual things. random sample of independent observations. That's basically your going assumption for all statistics, and it's almost never perfect, but we can do fairly well trying to get at least a representative sample most of the time. Then we have, we're going to need this time a normal distribution within each of the groups, which is a little bit more of a stringent assumption. Fortunately, this isn't going to matter most of the time because, although this is an assumption that we use to calculate the test statistic, it turns out that the analysis of variance will work even if we don't have nice normal population distributions to work with. But you should check it because if there are very gross or large violations of this assumption, you may need to do another test because you may not be able to trust the results of the ANOVA. So again, the way we do that is we look at our sample distribution, and if it's approximately normal, we say, okay, well that suggests that it could have come or may have come from a normally distributed population distribution, so it's probably safe to proceed here. If that sample is really non-normally distributed, then we would say, okay, it might have come from a non-normal population. Basically, we're just, using inference though. It's not a perfect process. Obviously, there's, potential issues with the logic there. Just because you have a normal distribution doesn't mean that it did come from a normally distributed population and vice versa. All right. So we need to check our sample distributions within each of the groups. And then finally, we'll need to check whether we have independent samples in each group if we have a between subjects design. So for this between subjects stuff, we need to make sure that we've actually put independent random samples in each of the groups. So we don't want people within the samples to depend on one another, and we don't want the groups to depend on one another. So that's different from the first point. All right. And then the last one here is homogeneity of variance, which means that we need each of the 3 or 4 or however many groups we have approximately the same variance in each condition. When did we see that assumption before?
For pooling?
When we pooled the variance, and that's because ANOVA is going to implicitly be pooling the variance to calculate the within subjects variance, or the within groups variance. So when we calculate within groups, we're going to be implicitly pooling our subjects. So we need to make sure that each of the groups has approximately the same variance. All right, so those are the tests. Those are the checks you have to do. Nothing in here should be new to you. These are all things that you've had to think about before. So I'm not going to go on them too much more, but know that that's the preliminary process that you should always go through. All right, so when we actually need to calculate our F statistic, it's fairly involved. But, it's not incomprehensible. So we're going to have to calculate these 2 variances, or mean squares, right? To get our F statistic. So if you think about this a little backwards, you want this F statistic over here, which means you need these 2 variances, the mean square between and the mean square within, or error. And then basically we know that a variance is a ratio of a sum of squares over degrees of freedom. So that means we also need our sums of squares and our degrees of freedom for each of those variances, which is basically everything that's in this table. The other thing we calculate is the total sum of squares, which is basically this exactly. So if you have xi being all of the observations in your sample, that's what gives you the total sum of squares. So it helps to kind of organize this information because we're going to be doing a lot of different calculations here. So as you proceed through these calculations, basically what you want to do is fill in each value you get into the appropriate spot in the table, and that will help you make sure you keep your calculations in the right place, and you can then calculate your F statistic just from the stuff that's already in your table. Also, this is fairly standard. You'll see this kind of organization in most software output. And, even research papers will use this format sometimes to present their results. You will see this around. All right, so let's look at each of these. So sum of squares between. This is going to be describing the variability between the groups. So to draw a picture here, if we have our between groups variance, we're looking at our different distributions. Sorry, those are comparable distributions, but we want to know how much variability there is between these different means. Okay, so what we're comparing here is not the individual scores in these groups, but we're looking at how much variability there is among the means of the groups, and this is going to give us our between groups variability. So if you're thinking about that and you look at this formula, it may help you remember it a little bit better. So basically, we're calculating a variance where we treat those means as kind of like our set of scores. And then we compare, or we subtract those from the grand mean to kind of estimate how much variability there is among the means. So this deviation score here, you have, first thing you do is you take each of these group means and you subtract the grand mean. So you're looking at these as your deviation scores. And then you're squaring those like you do in every sum of squares. You get a square. And then you're just multiplying this difference by the number of people in the jth group. So in our case, it's simple because all of the groups have the same number of people in it, so we can multiply at the end of getting the sum. But sometimes when you have different groups or different sized groups, you'll need to actually multiply this in your after you get each square. And the reason we do that is we want to basically count all of the observations, even though we're looking at the same mean. All right. So the next step, of course, to get our mean square is going to be just to divide this by our degrees of freedom. I think we said all of this. So here's an example. So in our data set here, we have group means 11, 12, and 4, and we have our grand mean of 9. So basically what we want to do is we want to just take the difference between each group mean and the grand mean, square it, multiply by the number of people in that group, and create that sum. So that's written here. So we have this group mean minus 9, so 11 minus 9 is our first term, square that, then we multiply by 4, and then we add the next one, and then we add the next one. So the last bit here is just to add all these up, right? And we're going to call this sum of squares between, is that an explosion? It's a chemistry class, maybe. Pretty cool. I don't know, I had a chemistry teacher in college who pushed it up every time he got the opportunity. It was like his favorite thing, which made everyone really happy, of course, so it worked. But you'd hear anywhere in the building every time it exploded. You'd be in the middle of math class and hear an explosion. You'd be like, oh, yep, Dr. Pawlowski's at it again. Anyway, so kind of used to explosions. All right. So does this calculation make sense to everybody? We've got the group mean and the grand mean, and subtracting them, and then weighting that by the sample sizes to get the sum of squares. Good. This is the easy one. Let's go ahead. So we crunch those numbers. We get 52. We're going to plug that into our table in a minute. Yeah, no, we'll wait. I don't want to write it on the board. We can just keep going. All right. So we've got next. Our sum of squares error, or within. So this is going to be the variability within the groups. So this one here, this was between these means. This next one is going to look within each of the groups. So within this group, and within this group, and basically we're going to be pooling that variance. So we're going to estimate variance here, variance here, variance here. We're going to combine those estimates, and that's going to be our within our within groups sum of squares. So to put that in notation, our sum of squares error. I'm going to try to call it error, but it's also within groups. The reason for that kind of distinction is that when we do within subjects design, it gets a little confusing to talk about within groups variance, and within subjects design, it gets a little challenging because we'll also have the sum of squares subjects, which makes it even messier. So I'm going to try to call this error, but remember that this is your within groups sum of squares. All right. Okay. So we want to, with this one, since we're estimating variance within the groups, what we want to do here is we want to compare each of our scores, xij, with the specific group mean that we're dealing with. So our deviation that we're interested in here is going to be each score, xij, minus, what do you think we're subtracting? The mean of the group, so x bar j. Good. And then we need to basically do that for all of the scores and all of the groups. So we only subtract the group mean that this belongs to. Technically, this should be written as a double sum, but forget it. Just know that you do this once for each score. So for each score, you subtract its particular group mean, and then you add those up for all of the scores. Make sense? We'll do an example in just a second. All right, so basically, obviously we're squaring those, sorry about that. Basically, once we get this one, we get a mean square error, and then we're almost set to go ahead and calculate our F statistic. So here's an example. So for the first score there, we're going to subtract, what do we subtract from 10? 11. Oh, shoot. Yeah, that should be,
Dun dun dun.
It's squares.
yeah, it's fine. But yeah, that should be 11. Sorry about the typo. I thought I fixed that. Guess not. All right, so I'll write it out. Why not? So what we want here is the sum of each score. So we'll go through all of the scores. We've got 10 minus 11, because that's its group mean squared. Then we add, what do we add? 11 minus 11 squared, and then we add, this is such a
8 minus 11 squared.
8 minus 11 squared, and then we add
15 minus 11
15 minus 11 squared.
Squared.
And what do we add next? Yeah,
12.
we go to the next group, and we have to move to the next group mean. So it's going to be 12 minus 12 squared, and then we keep going here. I'm not going to write all of these out, but know that we are just literally pooling everything. We're putting everything in one sum here. We do each score minus its particular group mean, and then we go from there. Make sense? All right. So when we square all those, add them all up, we get 54, and yeah, so there's that typo there. Make sure you make a note of that. And good. So that's our sum of squares error. We have one more sum of squares, and then we're done with the sums of squares for a little while. And this is just our initial variance. And the way we write our variance here is just using our new notation. So we add the differences of each score. This is now how we write all of the scores, minus the grand mean squared. And then, yeah, to turn that into a variance, we'd still be dividing by the total number of people minus 1. But we don't usually do that step, but you could. So this is what we call, this term here on top is what we call the sum of squares total. Okay. But this is one you've done before. Alright, good? Questions? All these sums of squares make sense? Alright. Josie's smiling because she knows that she's going to hear all of the questions tomorrow and not in class. At least I assume that's why she's smiling. Alright, so we have this nice rule here. So this is why we calculate our sum of squares total. The sum of squares total will be equal to the sum of squares between plus the sum of squares within. If it isn't, you did a calculation wrong. You need to check your work, figure something out. And there are a lot of places to fudge up with this. So, for example, if I had, accidentally written an 8 there instead of a 9, I would have gotten a totally wrong answer. I would have noticed it though because my sum of squares would not match my sum of squares total. So this little rule is a great way to catch mistakes. It doesn't guarantee that you will catch mistakes. It's possible to mess up your sum of squares between and your sum of squares error in such a way that it checks out anyway. But that's pretty rare. It doesn't happen very often. I have seen it happen a couple of times, however. But if you at least do this check to make sure that you're doing things right, that's a good place to be. You've at least done a really easy thing to do to check your work. All right, sound good? Question? Question? I'm just talking. Cool.
She asked if there's a bar above that.
Above, yeah, sorry,
Yeah,
my bars aren't showing up very well. PowerPoint's kind of annoying like that. But yeah, wherever you see x of g or x of j, assume there's a bar over it. Because it doesn't make sense to talk about the score or the score j. Those are never things. So those are neat. I'm sorry about the way that that's showing up. PowerPoint looks fine on my computer, and then as soon as I go to present it, it like moves things. All right. So here's how we calculate that. Basically, we subtract the grand mean from everything, square them all, add them all up. This is just like what we did when we calculated the variance. And then you get a number, which is 206. And we can do our little check. So 152 plus 54 is 206. And good. Like that. All right. Make sense? Alright, so we can plug those into our table now. So notice in our sum of squares column, we put in our between groups. Sum of squares, we put in our error sum of squares, and our total sum of squares. Sound good? Alright, so next, obviously, we need our degrees of freedom so we can get our mean squares. So let's think about this a second. So for our between groups, degrees of freedom, we have the number of groups minus 1. And if we think about that, it's when we calculate our between group sum of squares, we're treating these means as our sample, basically, and calculating deviations using this and comparing those to the grand mean. So basically, we have the same number of observations as we have these groups. So here we have the number of groups, and then we're calculating one grand mean. So we have the number of groups minus 1 for that term. So the notation for this is going to be n sub j. So no, I'm sorry, that's wrong. Never mind. We'll just call it the number of groups. Ignore that. This is going to be the number of groups minus 1. So how many groups do we have in this case? 3. So what are our degrees of freedom between? 2. Good. So that hopefully makes sense. And then how about our sum of squares error? How many things are we starting with? 12. 12, the whole sample size. So our total n is the number of things we're starting with, and how many means are we using? 3. N minus n groups. Okay? So if you really understand the concept of what a degree of freedom is and how you lose one, then this really helps you remember these things. If you don't, then you can get by, just memorize these, and you'll be good. So we've got total number minus the number of groups, and that's our within or error degrees of freedom. All right. And the last one is just what it's always been, the total number of observations you have minus 1. So that's going to be just 11 in this case, 12 minus 1. We also have this lovely property again for our degrees of freedom. So our degrees of freedom, degrees of freedom total equals the degrees of freedom between plus the degrees of freedom for the error. So if we add up those things, we get the total degrees of freedom. That's a great way to do a little check to see if you got your degrees of freedom right. Hopefully you don't get them wrong, but if you misremember one of these formulas, that can be a good way to kind of spot that and say, hey, I need to think about this again. All right. Questions on degrees of freedom? Okay, so let's fill them into our table here. Our degrees of freedom that we calculated before, 3 minus 1 we said was 2. The degrees of freedom for error, we said we have total number minus 3 is 9. And then our sum of squares total is 11, so 2 plus 9 is 11, we're good. And we can plug those into our table. All right, so how do we get our mean squares from here? Yeah, we're just going to divide out. Excellent. So we divide across the rows here. So we take that sum of squares from between, divide by the degrees of freedom between to get the mean squares. We don't do anything for the total because if we do, we just get the total variance, and that's not really that meaningful when we have these different groups that we're interested in. It's also kind of standard output in other parts of like the statistics process, so we don't really worry about that too much. All right, so let's get those mean squares by dividing by our degrees of freedom. I should also note we do not have a nice addition property once we've divided by our degrees of freedom. So some people like to check their work again overzealously and incorrectly by seeing if their mean square error plus their mean square between equals their mean square total. It doesn't. It won't almost ever. So don't bother with that. It doesn't work. Only for your sums of squares and your degrees of freedom. Once you divide, those things are no longer related in a very nice way. So let's divide out. So we said 152 over 2 gives us our mean square between, and that's going to be 76. And then our mean square error is going to be 54 over 9, which is 6. Which is 6. So we can plug those into our table, which I did not apparently do, but you can easily imagine having 76 and 6 plugged in there. And then to get our f, what do? We want the ratio, right? Which one goes on top? The between is going to go on top, and then we have error in the bottom, because we always have error in the bottom in statistics. So, in t-test, we divided by standard error. In t-test, we divided by one of several options for how to calculate the standard error. In f-test, we're also going to be dividing by error. So here we have our between over our mean square error, and that will give us our f statistic. So in this case, that's going to be 76 over 6, and we get 12.66 as our f value. All right, so next we need a critical value, or a p-value. So f is actually a little bit nicer than t and z in terms of drawing your final conclusion. We said that last time we said our f distribution is actually this kind of funky skewed distribution. It'll have different shapes depending on our different degrees of freedom. But don't worry about that too much. It'll be taken care of when we use the F tables, just like it was with the T tables. We just go to the right table, look up the right degrees of freedom, and we get our critical value just like we did before. But basically, we've got this funky skew distribution. We said that if there's no difference, we'll get a value that's close to 1 here, right? If there's a difference between the groups, we'll get a value that's bigger than 1. And we're going to kind of compare our F statistic to the expected value of 1 by seeing, well, is it much bigger than our value? And the way we do that is, well, we can set an alpha to be like 5% or 1% or whatever we're using, and say, okay, well, there is an F critical value that cuts off that percentage in the tail of this distribution. So once we look up our critical value, we'll reject our null hypothesis. Remember from last time that the null is that the groupings are all equal if we get a value that's bigger than the critical value. So notice in this case, we don't have to worry about it possibly being more extreme and negative. It'll never be negative. Why is F never going to be negative? It's a ratio of variances. And what do we know about variances? They're always positive because we're squaring things. We always have this little squared here, so those are always going to be positive. I have never yet seen a case where people have imaginary data, so we don't need to worry about variances that are negative. All right, good. So we have our critical value. If we get an F statistic that's bigger than that, we can reject. You can also calculate a p-value. So this shows alpha and the critical value. We can also draw a similar, or rather the identical distribution, but label different values on it. So if we say we got an F of 1.2 or something, we could calculate, or actually let's use our actual F value. What is our F value?
12.6.
12.66. Does that seem bigger than 1 to you?
Yes.
Yeah.
Yes. So if we do this test and it turns out that it's not significant, we might want to check that. So this seems much bigger than 1, so it probably is, but we still need to look at our F table. So what is this area here that I've shaded past 12.66? Yeah, this is our p-value. Good. And if the p-value is less than 5%, our alpha value, then we will reject our null hypothesis. If the p-value is greater than our alpha value, then we fail to reject. So same thing as before. All right, good. Questions? Yes.
So you said is the p-value close to what?
Alpha.
If p is less than alpha, then you reject. Or similarly, if your observed F statistic is bigger than your F critical value, then you reject. Good? All right. So this is what an F table looks like. Sorry, the text is really small there, but if you can see, the top there has degrees of freedom 1, and it says degrees of freedom in the numerator. And then the side says degrees of freedom in the denominator. These will sometimes be labeled a little differently, and I don't remember if these are the same or different as the ones that you have. You can check that online, and you can check also the tables for your final exam are posted, so you can practice using those if you want. Yeah, so what are degrees of freedom in the numerator? Which degrees of freedom are those? Yeah, the between. So when they say in the numerator, they mean the between subjects, the between groups, degrees of freedom. And then when they say in the denominator, they mean the degrees of freedom for the error. There will always be some sort of error in the denominator, so you can usually assume that the denominator degrees of freedom are the error degrees of freedom. The reason I have it set up as numerators and denominators because you'll use this F table for other kinds of tests. Well, you won't, but you can use this for other kinds of tests. For other kinds of tests. So that's why they have it labeled kind of vaguely, but don't let that confuse you. Some tables will label it more directly. They'll say degrees of freedom for the error and degrees of freedom for between groups or difference between means or something like that. Some of them will even say number of means -1 or number of means. You just have to read the table to figure out those degrees of freedom. All right, so in this case, we have 2 degrees of freedom in the numerator, and we have, sorry, what are our error degrees of freedom? They were, there it is, 9 in the denominator, so we go down to the 9th row and over to that second column, and we get 4.2565 as our value. So that's pretty straightforward, I hope. Which basically means that our critical value here is 4.65, and then our observed F value here is going to be 12.66. So this whole area, this is our alpha value. This stripy area here, this is our p value. So we can either say 12.66 is greater than 4.65, or we can say 5% is greater than our p-value, which is this area here. And clearly this whole thing, this alpha, is bigger than this little area, this p-value. Good. We didn't calculate this p-value, so you probably want to go with this explanation. But they're the same in principle. Make sense? All right. So what do we conclude? What are our next steps? Those are 2 questions. You can answer both in one or reject the null. We're going to reject the null. Good. Because our critical value, our critical value is less than our observed F. So what does that mean? What was our null hypothesis again?
That the means are the same.
Yeah, our null was that mu1 equals mu2 equals mu3, and then our alternative was at least one is different. Okay, so that means here we want to say, well, at least one of the means is probably different. So to word that kind of more formally, we want to say something like, we conclude that some of the treatments, were significantly different in terms of their effectiveness or something. That writing is kind of funky. I don't know what I was doing there. But basically we want to say something along the lines of there was a significant, meaning statistically significant difference between the groups. So do we know which group is different? We don't know. We can make a good guess though, right? We looked at the beginning and we saw that one group was much, seemed like the scores were lower than the other 2 groups. So we can make a good guess, but we don't actually know yet. We need to check and make sure. And the way we do that is with follow-up post hoc tests. Let's see how we go. So,
Question?
question, yes.
Oh, you said that we didn't calculate the p-value, but would we do that? And if we did, how?
You can't with the tables that you have.
Okay.
You might know it if you're given software output.
Okay.
You could also look up your F value using an online F distribution calculator or something like we did with the T values.
Okay.
But no, generally you'll have to use these critical values on exams.
Okay.
If it's for homework or something like that, you could go and look up a p-value, or you could use software to check your work, and the software will automatically give you a p-value. So you will, in real research and real work will work with the p-value whenever you can, rather than these critical values.
Okay, thanks.
Alright, so we need to basically go in, now that we've had a significant F test, and say, well, what groups were different? So you can kind of think of the analysis of variance as sort of giving you permission to go and look at the specific group comparisons. And we said that we do that because we want to keep our error rate low, and we also don't want to do lots and lots and lots of t-tests when we can just check everything all at once. Alright, so let's think about these follow-up tests. Sorry, not last time, but today, we just saw this. We had this result, which gave us a significant F test. So our groups are different. We need to figure out how they're different and how much difference is there relatively speaking. So one thing we can do is figure out, basically by knowing these group means, how much of the variance were we able to explain in the outcome. So basically we say we have this kind of this one. Oh, I erased it. Never mind. We have kind of the overall variance of all of the scores. We also have this variance within the groups and the variance between the groups, where we know the group mean in each case. Basically, what we want to know is how well were we able to predict scores given that we knew which group they were in. And that's what we mean when we say things like how much of the variability were we able to explain. So, and of course we need to follow up with t-tests, but before we do that, let's do effect size. So we talked about D-class effect sizes before. Many of you need to go review that, by the way. But we also have eta. So eta is our first R-class effect size. We'll talk about two more next time. But eta squared tells us basically what percent of the variance in our outcome variable did we explain by knowing group membership. So basically, if we know what group you're in, how much does that help us predict how many symptoms you'll have for the disease we're treating? So theoretically, we should be, by knowing whether someone's in a control group or medication 1 group, we should be able to better guess how much improvement or how little improvement we'll see as a result of this study. And that's what eta squared tells us, and this is how we calculate it. It's going to be the sum of squares between over the sum of squares total. Equivalently, you can say the sum of squares total minus the sum of squares error. You'll see it both ways, and it doesn't really matter for now which way. Good. Anyway, so here's kind of that written out, what that means. So the proportion of variance in the outcome measure explained by knowing group membership. So in this case, we want to say that our eta squared is the proportion of variance explained in the number of depression symptoms, given that we know what group or what treatment condition people receive. So given that we know which medication they received. All right. So in this case, we can calculate that by taking our sum of squares between over our sum of squares total. Sorry, I think this example is using slightly different data. These numbers are a little different. Don't let that confuse you. But basically, it's just that sum of squares between over the sum of squares total, and we get a percentage. I apparently didn't write it down. Can somebody crunch that real quick on 32 of 106? Everyone in this room has a calculator.
0.7096.
0.7096. Okay, so that means we explained about 70.9%, or you said 96?
So about 80%, or 71.
71%. Let's go with that. We explained about 71% of the variance in the number of depression symptoms people had by knowing which medication that they received. So that's how we would interpret that. A lot of people, when they were interpreting their DCOS effect sizes on the exam, forgot to incorporate that context. So you got half credit for that, basically. So you could say, well, eta squared is the percent of variance we explain in the outcome by knowing the group, or you could say the percent of variance in the number of depression symptoms people had given the medication that they received. So we're just filling in what we mean by in the outcome and group membership. We're filling in our actual context when we interpret these values. We don't want to just spit out the definition when we're interpreting things. We want to explain what we're talking about. All right. So that's kind of all preliminary to this set of follow-up tests. But it's also something that is very important. But let's go ahead and talk about these key tests. So sorry if that was, I guess, a little bit of a tangent, but let's get back to the t-tests. So we said last time we also have these planned comparisons and we have kind of unplanned comparisons. The planned comparisons we refer to as a priori comparisons or a priori hypotheses, meaning we planned them before we looked at any of our data. We said before we looked at any of our data that we wanted to compare the control group with treatment 1 and the control group with treatment 2. That's a possibility. If you, have specific things in mind, you're going to use this kind of a priori approach to test your hypotheses. However, if you, have a lot of groups, you may not be able to anticipate which things might be interesting to look at. So, you can imagine somebody having like 5 or 6 different conditions, and they might only after they've looked at the data realize that some of them seem kind of different. So they might, in that case, decide after they've looked at their data that they want to compare a couple of groups that they didn't think of before. In that case, they'd want to use these kind of post hoc comparison strategies. So post hoc means after the fact comparison strategies. So the reason we have to take it, well, let me ask you, why do you think we have to take a different approach if you come up with hypotheses after you've looked at your data?
Because the data is going to change your hypothesis.
Okay, your data is going to change your hypothesis. Why might that be a problem? Yes.
Maybe the same effect as like a double-blind study type thing.
So looking at your data would influence which groups you decide to compare. Yes,
yeah.
That's the root of the problem. But what specifically will that cause?
Like your data could be an effect of randomness, so you could have your hypotheses influenced by randomness, not by information.
Right. So if there really is like no difference between your groups, they could still, due to random sampling, appear different. So let's say you have 3 groups, and these groups in reality are actually all the same, but for some like group of sampling, one of them is extreme in one way, so we get a mean here. Let's say, let's say 1. Let's say group 2 is 3. It's average. So these are going to be sample means. Here. And let's say this third group is going to be 5. It's possible that we get these means sampling from a normal distribution with a mean of 3, right? 1 is kind of close to 3, 5 is kind of close to 3. But if you look at this after you see, or if you look at this data and then decide which groups you're going to compare, you're going to pick this one and this one. And it turns out those are the most likely to be different, but they might just be different due to chance. So basically, if you look at your data and then decide which groups to compare, you're increasing your probability of making a mistake due to chance, because you're picking which comparisons to do based on something that could be a random process or is a random process. Does that make sense? Yeah? So this is a phenomenon called capitalization on chance. This comes up in a lot of different applications of statistics, but whenever you're picking something, and that selection process is influenced by randomness, the probability of you picking something by accident basically becomes higher. So you increase your probability of making mistakes just due to chance. We'll come back to that, especially when we get to regression, hopefully next time. All right, so these two approaches are going to be different. Because of this capitalization on chance issue, when we do post hoc comparisons, we're going to need to be a little bit more rigorous. We're going to need to take more steps to keep our error low. So we might want to do things like Bonferroni corrections or Tukey tests, which basically provide more conservative tests of our hypothesis. So for example, Bonferroni tests reduce your alpha level by dividing your alpha by the number of tests you're going to do. So instead of having alpha of 0.05, you might have alpha of 0.05 divided by 3, and you have to meet that more strict threshold to proceed. Tukey tests are similar, and I'm going to not cover those in here, but I will cover, or rather I post, or haven't yet, but I will post kind of a reading on these post hoc tests. So the Winters Bonferroni and Tukey tests. There are actually dozens and dozens of these, but those are the only ones you're going to learn. And you can read through that, and that will basically give you an outline for how to do the homework questions that ask you to use these. We will go through this planned comparison in here, though. Just for time's sake, you're going to have to take some of this home, because there's really a lot. You can spend, almost an entire quarter studying this stuff. All right, so when we have a priori hypotheses, that's the nicer case. We can just do something quick. We can use our mean squared error to calculate basically a standard error for our t-test. So we said that that mean squared is an error variance, basically. It's a variance, and it's describing the error that we have. And it turns out that that's very nicely related to our standard error. So the way we get our standard error for our t-tests is just we multiply that mean squared error that we get by 2 and divide by the number of observations we have in each group. Note, this is going to be a little different if you have different numbers of people in your different groups. We're not going to handle that case, but note that you could do it very easily, and if you want to talk about that, we can talk about it in office hours. Most of you can probably figure it out if you think about variance sum law, what this actually looks like. So, actually, no, forget it. I'll just show you. That way, I have fewer questions in office hours, and you guys don't have to figure it out on your own. So we have, we're combining basically our two groups. We're doing independent samples t-test here, right? Because let's say we want to compare group 1 with the group 3 mean or something like that. If we're doing independent samples tests to compare those, we said, well, our standard error is going to be the square root of our pooled variance over n1 over n2. If we have the same number of people in each of those groups, we have our mean squared error here on top, n sub j on bottom, plus our mean squared error on top, plus n sub j on bottom, and that gives us 2 times mean squared error over the sample size. This also gives you a way to compare groups when you have 2 different sample sizes. Instead of n1 and n2 both being n sub j, have n1 and n2 being whatever they are. So that's the more general case. And again, here we're saying that the mean squared error is the pooled variance. Make sense? If not, don't worry about that too much. You can get by just knowing that formula, but this will help you kind of understand that we're still doing the same thing that we were doing with the t-test. We're just kind of picking a shortcut to get our mean squared error. We no longer have to calculate the pooled variance because we've already done it. All right. So as I said, you're going to do these post hoc tests in your homework, but learn how to do each and let me know if you have any questions. All right, so here's an a priori comparison. So let's suppose we want to compare medication 2 to the control group using a t-test. So we said our means, yeah, this is using that different data or something. But anyway, the mean squared error here is 6, and the two groups we're comparing each have, where's the mouse? The two groups we're comparing are the control and medication 2, right? So they each have 4 observations. So n sub j is 4. So we have 2 times our mean squared error, which is 6 over 4, and that gives us a standard error of 1.73. And you'll have to recall the notation for the standard error when you have differences between two means. It's going to be S subscript the means you're comparing. So if I'm comparing the control group to the medication 2 group, it might look like that. Makes sense? So the difference between the means is the subscript. So I know that confuses people sometimes, but that's all that says there. So that term there is just the standard error. And then to calculate our t, we just plug in those differences. So we have x bar 1, so there are bars here again, x bar 1 minus x bar 3 over the standard error. So just difference between the means over the error. It's pretty straightforward. All right, so that gives us a t-value of 4.46. Given what you've learned about the t-critical values you've seen so far, is that probably significant?
Yep.
Yep, good. The t-values, at an alpha of 0.05 are always going to be 1.96 or higher. So for two-tailed tests, we have something bigger than 1.96, but maybe not by a whole lot. And then something smaller than negative 1.96, but maybe not by a whole lot. And we compare those. However, we should probably look up our critical value, our critical value to see, because we do only have 4 observations here. Now that I think about it, it's not very, that's not enough really to draw any lasting conclusions. But I didn't look up the t-critical value here. You guys know how to do that already, so you guys can figure that out. So hopefully that's significant, but we should check and make sure. But yeah, what would that mean if it is significant? Yes.
Random minus 4 or random minus 3.
Oops. Yeah, sorry. I think that's just a typo. Or you guys can check on it and figure it out. But yeah, this should be the group mean of group 1. Yeah, I'll write it out. So we should have t equals x bar 1 minus x bar 3 over our standard error. So we have, group 1 is 11 minus 4 divided by the standard error. Sorry. So this would be 1.73. And then I don't know what that works out to be. You guys can check and make sure that's right. But the formula is correct. It's the difference between those two means. Good.
Can you email me about that? I'll
Fix it in the slides. Hopefully I'll also remember to fix that other typo in